Hello, and welcome to this creative coding workshop hosted by Synesthesia and Creative Code Art. We're psyched to be bringing this to you. My name is Theron Prey, and today I'm going to be teaching you how to make this. This is a shader running in Synesthesia. We're going to learn how to code in GLSL to write this bad boy. And by the end of it, you should understand almost every line of code in this shader, because we're going to write it line by line. So we're going to start with some simple shapes. We're going to work on some coloring functions after that. And then we're going to get into audio reactivity. We're going to throw in some media effects and some feedback effects. All of that resulting in what you see right above me now. First things first, you're going to need to download these things. This is Synesthesia and a zip file with the scenes and media that we're going to be playing with today. So get those downloads started. And if you actually pre-registered for the event, you should be able to log in with your account, your email, and your password. If you didn't make an account, then you can log in with your email, and the password is your email. And so y'all who pre-registered, you have full access to Synesthesia for a month to try it out. If you didn't pre-register, no worries. You can still join us on this. Just download Synesthesia. You can use the trial, and you're going to be able to code right along with us. Everything that we're going to be doing today will work for you as well. So while you guys are downloading these files, I want to actually start by talking about what shaders are. And the best place to start for that is actually this little demo video that just explains it very well. This whole video is awesome, and you guys can totally go watch that after this workshop, and you'll learn a ton more. But the intro here is actually just a great explanation. So let's start here, and I'll let Kishimisu take it away.
Have you ever looked at a breathtaking digital art piece and deeply wondered how they created that? There are many different approaches to digital art, but shaders might be one of the most powerful and versatile when it comes to creative coding. Shaders are like the paintbrushes of the digital age. They allow you to turn a blank screen into a stunning animation in real time, and they're responsible for the stunning visuals in some of your favorite video games and movies. They can be used by creative developers in order to make 2D and 3D renderings exclusively using code, their imagination being the only limit. Shader art coding is all about using mathematical functions and algorithms to manipulate pixels and create incredible visual effects. It's a unique fusion of art and science, where creativity and precision collide to produce something truly mesmerizing. But what are shaders, you may ask? In essence, shaders are small programs that run on your graphics card and are responsible for calculating the color of each pixel on a canvas. Shaders work by taking inputs, such as the position of the current pixel, and using them to calculate a single final color using the OpenGL shading language, or GLSL in short. It can be seen as a mathematical function that maps a 2D coordinate, the pixel's position represented as X and Y, to an output color which in computer graphics is represented by a red, green, and blue channel. This function is computed in parallel for every pixel on the screen, which means that shaders can perform millions of calculations per second to produce stunning real-time graphics.
Okay, so there's a really critical part here that I'm going to just rewind to, and we're going to look at one more time. So what he said there is that fundamentally what the shader's doing, it's a program running right on your GPU. It's taking in an XY position of a pixel on the screen, and it's turning that into a red, green, blue color. So that's true of every fragment shader, every pixel shader that we're going to be creating today. It's going to start with this XY position of a pixel, and then we're going to do a bunch of math and turn it into a color. And in addition to that, so that's kind of the starting point, what Synesthesia adds to the mix is that there's also audio variables. So these are going to be things that we can drop right into the code to get something like the Syn base level and animate things in our shader using tied to the audio that Synesthesia is picking up. And the other kind of input is going to be live controls. And so we'll look at that in a sec when I show you guys Synesthesia. So just remember that. Everything we're doing today, we're taking these input variables, this XY position, audio variables, and controls, and turning them into a color output. And that's how shaders work. You guys should have Synesthesia downloaded and installed now. Let's go ahead and log in over here. I want to give you guys a good kind of overview of the software, what it does, and then we'll be spending the majority of the time today over here in the integrated development environment or the code editor. But first off, let's just look at Synesthesia. When you open up Synesthesia for the first time, you'll land on the scene library. And these are all the scenes that are built in or that you've downloaded from the marketplace or your custom scenes that you've loaded in. They'll all appear here. You can go ahead and click around and try some of these out. You'll see that they should be already reacting to audio. That's one of the most critical things in Synesthesia. One of the first things you want to do when you open Synesthesia is get audio input running. And so either your laptop has a built-in microphone, in which case that should appear here, or if you're on Windows and you want to run music into Synesthesia, you can also choose desktop audio and then just put on music, you know, with Spotify, whatever. And if you've chosen desktop audio, then that will come through. And so if you want, you can just click visualize audio and make sure that you're getting an audio feed. As you can see here, I am. So I can stop audio visualizer. Cool. Now come up and click on this top tab over here. That's how you get to the control panel. Here are the scene controls and the meta controls. And then down here you have media that we'll get to in a sec. But for every scene, there's a unique set of controls that allow you to manipulate the visual in real time. And if I change scene, you'll see that these controls also change. And these ones don't, because these are the meta controls that apply the same way to every scene, no matter what. As I said, every scene has a unique way to react to audio and a unique set of scene controls, and also a unique way to interact with media. So if you just click on demo media.mp4 in here, and you can use that to, just kind of test how scenes look with media. But even better would be to load in your own media. The way to do that, luckily, I've given you guys a little sampling of some demo media. So this has some images in it and various videos that are just kind of good starting videos for using today to play with. So we're going to load that media into here. Just click right here, add folder, and then navigate to the Syn GLSL workshop files, Syn demo media. And then just select this entire folder. So you don't select the individual clips, just select the folder. It'll show down here, click select folder. And now boom, you see that those videos are loaded up in here. And if I run different scenes, you can see that the videos are mixing with the scene in a unique way. So the one other important setting to set is come over to the settings tab and scroll down until you see scene folders. And then just click on add folder. And you're going to want to pick the Syn workshop scenes folder that came in the workshop assets that you downloaded. And then you don't have to pick the scenes inside it. Just select this whole folder and then click select folder and click primary. And then come over to library And now you should see this scene and this scene. And this one's actually the end goal for the workshop today. Let's get our coding tab set up while we're still here. And in order to do that, just going to be a few settings to set. Come into here and uncheck this Use External Editor box. We're going to want to use the built-in editor. And then come down here and for auto compile, put that on save. That's just going to save us some time. Every time we hit Control S, it'll auto run the new code and we can see the code changes that we made. And finally, I like coding with suggestions off. It's up to you, but I like coding with it off because I'm familiar with the variables and I don't want it to kind of be messy on the screen for you guys. But if you'd like to leave those on to remember some of these variable names, totally works too. You can always find them here in settings. So now that we did that, come up here and click Edit on this scene. And now you see we can actually type in here and undo all that. And you can hit Control S to save your changes and reload the scene. And so before we get started, why don't you just open up a notepad or any text editor, code editor, whatever. Do Control A to copy all of this and Control C. And just paste that over into like Sublime. Just paste it over into a notepad so that you can pull from it. If you ever get lost during this, you can just pull in the code that we're eventually heading towards. And it could help you, get there faster. So, cool. Now that we have this set up, I'm going to put this scene away, and we are going to start fresh by coming back to this library tab, clicking New Scene, and you can see we're already in edit mode on this new scene. So this is what you start with here. You can see it's got some kind of gradient on the x-axis and the y-axis, and it's actually got this slider. If you move the slider up and down, you can see that's controlling the visuals. For now, I'm going to delete everything in there. We're going to rebuild it from scratch. And so let's start by just talking a little bit about GLSL types, because these are the 4 most important types that we're going to use throughout this workshop. And that's float. My float equals 0. A vec2. My vec3. And you can probably see the pattern here. My vec4. Okay, so these are the 4 types. A float is just a number that's not an integer. It's got a decimal place. A vec2 is just 2 floats that are stored together in 1 variable. And a vec3 is just 3 floats that are stored together in 1 variable. And a vec4, you got it, it's 4. We're not going to be using vec4s much. Vec2s and vec3s we're going to use a ton because vec2s are really good for storing x, y position because they have 2 numbers stored in 1 variable. Vec3s are really good for storing color because it's RGB. And shaders are basically, and GPUs in general, are optimized to any math that they do on a float, they can do on a vec2 or a vec3 in the same amount of time it would take them to do on just 1 float. So that's called vector math, and that's kind of what's happening under the hood and why so many shaders work with vec2s and vec3s. But it's also just because it's, the reason we use vector math in the first place is that colors can be stored as vectors really conveniently, and positions can be stored as vec2s, right? Oh, and real quick, this is super important. Down here is the console output. So just click on that, and then you'll see every time you save your scene,
or rerun it, you'll see down here, if it loads successfully, it'll tell you. If you make an error, you will also see that down here. And so this is telling you about a compilation error. And right here, inside the parentheses, is the line number that it occurs on. And so here it's telling us there's an undefined variable. So you're going to be wanting to see green, and if you see red, come down here and check out what error you've made.
Cool. Let's write our simplest shader ever. We're just going to return a color. As I said, that's the whole point of a shader, is to return a color. So this is the simplest shader you're ever going to write. One thing that could be confusing right out of the gate is just that this is a vec4 instead of a vec3, right? I was talking about color as RGB. This color as the last one that we return has to have an alpha channel too. So it's actually RGBA. Just put 1 there. It's okay if you put 0 there. It doesn't matter for right now. But just put a 1 in there, and then we'll never really be working with vec4s for the rest of the lesson too much. So, okay, so that's returning red. There's green, right? Now, how can we make this more interesting? Well, let's go ahead and reset this to black. Now, I want to make it vary based on position. And so the way we're going to do that is by making a new variable called position. And we're going to set it to _UV. So UV is just a convention in shader land. You'll see UV in a lot of people's shaders. It just means XY. It's the same thing. U corresponds with X, V corresponds with Y. So just if you ever see UV, just think of it as XY. So we have a position variable, and on the red channel, let's do position.x. So everybody should be at least to here. And what is going on here is we've got the XY coordinates here saved in position, and X, the way that this plot works basically is it starts at 0 down in the bottom left here, and it goes to 1 in the top right. So if we did position.y over here, you can see that's now a gradient on the green channel using the y axis variable, right? Position.y. And if I do them both together, that's what you get. So this is kind of a plot of the position variable. So it's 0, 0 down here. That makes sense because the color is actually black. And up here, the color is yellow because it's full red and full green. And everywhere else, you're getting whatever that pixel's coordinate is, right? So right here, it's going to be 0.5, 0.5. Down here, it's going to be 0.5, comma, 0. So basically, the shader is loading in this is a different number. This is a different set of numbers for each pixel on the screen, right? And that gets loaded into this position variable, and then we're coloring it based on whatever numbers that pixel happens to have there. So while we're right here, just for a moment, I want to introduce you to this other variable as well called UVC. And this is a different position variable. It's basically just a plot in a slightly different position, and it's also normalized differently. So I'm going to call this center pause equals UVC. And then instead of position here, I'm going to put center pause in. So the X of center pause is now in the red channel and the Y channel. That's what it looks like. So what is going on here is that this is normalized differently. And actually now 0, 0 is right in the center of the screen. And it goes to 1.0 at the top of the screen and -1 at the bottom of the screen. While in red, it goes to a little over 1 and a little and -1 over here. And we're just going to hold on to that because we're going to use it again later. But for now, I'll put this back in, and we're back to our gradient. So now I want to introduce you to the mix function. So let's add some new colors here. I'm going to add an orange. And I'm going to add a teal, maybe 0.1. You don't have to put in these exact colors. You can put in whatever colors you want. I'm just going to start with these. And I'm going to make a new variable called color out. And let's just set that to orange for now. And then down here, I can put in color out in place of those 3 channels. And so this is another thing you can do in GLSL, super convenient, where if you need to make a vec4, just because this has to return a vec4, you can make it out of a vec3, comma, and then add one more number. So this should show us orange on the screen. Boom. Now, if we wanted to mix between orange and teal, let's use the mix function. So mix between orange and teal. And so this takes a color and then another color, and then you put whatever the mix value is. So this is just going to be one number that controls how much orange versus teal we're going to get, and it'll smoothly mix between them. So let's put in green amount here, just since that's a variable we can use. It goes between 0 and 1. And now you can see we can smoothly mix between orange and teal. And if I want that to be a little more interesting, again, I can put in, how about position.y? Sweet. So we made a gradient between 2 colors and the position, and we made it vertical by using position.y. All right, let's add a circle to the center of the screen. So this is where center pause is going to come up handy. And this is where center pause is going to come in handy, since it's already centered. So we have this plot that goes from 0 in the center, and it goes to -1 in the bottom left, 1, 1 in the top right. Let's make a variable called float dist from center. And we'll get length of center pause. So this is a vector that is coming out from here, right? And the further it gets out from there, the higher this variable, distance from center, is going to be, because we're using this length function. So let's just see what that looks like real quick. And this is a super useful thing if you are ever a little confused about what a variable looks like. There's actually no print function in GLSL. So you can't just say like print, dist from center like you would do in some other languages to like see what that variable is doing. In order to see what it's doing, you've got to put it on the screen somehow. So something I'll do here is just I'm just going to use color out as sort of a debugger for a moment to just see what dist from center looks like. So I'm going to say color out equals vec3, because it has to still be a vec3 for RGB, dist from center in the red channel, and then 0, and then 0. Okay, cool. So that actually makes sense because it's 0, 0 in the center. As we get further away and dist from center increases, you get more red. And there's something kind of cool here too. I'll show you guys. If you ever want to make a vec3 where it's dist from center in all of these, you could do it like that. Or you can just delete the green and blue, and that's the same. It'll automatically, if you just pass in one number, it'll say, oh, I see, you want to make a vec3 out of that one number 3 times. So that's another little convenient thing. So as I was saying, this makes sense though. We have this dist from center being plotted, and if we wanted to give that a more hard edge, there's another function we can use called step. So to make it a circle with a hard edge, we're going to use the function step. And you might be asking, okay, we've got mix, we've got length, now we're introducing step. How many of these functions are there that are kind of the built-in OpenGL functions? And actually, there's just a handful, and there's so much that you can do with them. So step, mix, length, these are going to be some of your best friends. You're going to come back to them again and again. But if you're wondering what all these are, just search OpenGL documentation or GLSL documentation, and that'll take you to this page, and you can see the mathematics built-in functions. So there's like, you know, abs for absolute value, right? It's got the description right here. And we were using step, so that's this one. You can see it takes two variables. You have to put in an edge and an x. So you might read this and you might still be kind of confused. Like, okay, so if it's less than edge, it returns 0. If it's greater, it returns 1. But what does that look like? There's another tool I want to show you guys real quick. And you don't have to like use these every time, but it's just helpful when you're learning, helpful to visualize. And that's called GraphToy. So if you just Google search GraphToy, should be the first one. And this is something made by the same guy who made ShaderToy, actually. And so he's got a whole bunch of functions in here, but we don't need those. Let's just see what the step function looks like. And so for that, it's actually, you can see it right here. You can click on that if you want. But yeah, we don't need to. Let's say edge is going to be the first variable, and then x is the second. So this is what this function is actually doing, step. It's going from 0 here, and then right when you hit 0.5, it goes all the way up to 1, right? And if I made this 0.2, okay, the step is there, right? This is pretty straightforward. So if we step this function that we have here at 0.5, that should give us the same thing of 0 below 0.5. And any time this variable dist from center is above 0.5, it'll give us white, right? Or 1.0. So let's call this circle. And I'm going to say equals step 0.5 dist from center. So we're defining that edge at 0.5. And now, of course, circle isn't doing anything yet, so let's visualize that right here. Okay, so we got our circle. Rad. So let's say we wanted to bring our colors back in. We're just overwriting them right now by saying color out equals. And instead, in GLSL, well, real quick, I'll just show you. You can hit Control/ to comment out that line, right? And so that's a really easy way to bring a line of code in or out. But in GLSL, you can also do plus equals, and that will add the two together. And so you might be thinking, okay, this is kind of weird actually, because we're painting that color all over this, and then we're adding white over the top. Why don't we see the white mixing with the orange and teal? So the reason for that is because this shader only works up to 1.0. So in GLSL, if you return a color like 1010, right? So if I come down here and just say color out plus equals vec3 10 10, or just 10, right? Okay, everything's white. You can't get any whiter than 1.0 white. So it just doesn't do anything. It just clamps it and clips it off. And if I do minus that, okay, everything's going to be black. If I do minus 0.5, now we can see that that information actually was under the white that whole time, right? But it was just being clamped by the view screen, basically. So that's something to keep in mind when working with color in GLSL. So maybe if this, if this was going from 0 to 1, what if we made it go to 0.5, right? Okay. Well, we can do that by taking circle and multiplying this whole thing by 0.5. Okay. So now we can see the overall gradient, and the circle is still doing its thing. All right, we're going to pick up the pace a little bit here. And now I'm going to teach you about smooth step, and then we're going to use some synesthesia built-in functions to make more interesting shapes here. So real quick, the smooth step function is like step, except you put 2 numbers at the front. And that is where that edge starts and where that edge ends. And so you can see that here too. If I put in smooth step, say 0.2, 0.4, and X. So now between 0.2 and 0.4, it smoothly interpolates. And that's what you're seeing here too, right? So between 0.4 and 0.5, I'm getting a smooth gradient now. What if instead of it being just white all out here, I want to just make a ring, right? Well, for that, we can use the built-in function pulse. So you'll see GLSL native functions are in purple. Built-in functions are in yellow, and this is built into Synesthesia. So this is one of the other benefits of coding in Synesthesia versus some other softwares. You get a lot of built-in functions right out of the gate that are just nice to have on hand because you end up using them again and again whenever you're trying to make something in GLSL. So the way this one works, I'll actually just go ahead and delete all this. We're going to do a pulse, and this takes a variable dist from center and 0, and then it takes where you want that pulse, which is going to be 0.5, and then how thick you want the pulse, which is going to be 0.1. Boom. Okay. So if you were wondering how that works and like how I know that function works like that, you can click this button, Show SSF Docs, and then come over here to click on SSF Functions. And you can find all of these right here. So if I go to pulse, this tells me what the pulse function does. So the place within the pulse to sample, the center point of the pulse between 0 and 1, and the width or duration of the pulse. Cool. And you can see some of the other built-in functions here that Synesthesia has that will help you get up and running quicker. Okay, dope. We have a ring. Now, let's say I want to control some of the parameters of this ring, or maybe all of them, right? Well, I could introduce some new controls here. I'm going to call one ring thickness. And let's actually make a new control group for these. So for that, just click on this group. So yeah, to make a new control, click on this plus. Then in group, click on group and just type in ring, add group. Okay. And let's actually add another control. And this will be called ring radius. Let's add that to the ring group too. And another one called ring position. And this one's actually going to be also added into the ring group. This one's going to be XY, because in order to control the ring's position on the screen, I'm going to want to have both an X and a Y value, right? So I could make 2 controls, or I could just make it a type XY. And now let's save that. So if we look down here, now that just made these 3 controls, right? In the ring group, so this is a new UI group, and it also made variables that we can now use in the code. So in order to control this circle's spot, so let's do the thickness and the radius first. So the ring radius is actually going to go here, ring radius, and the thickness is going to go here, ring thickness. Okay, so let's check these out. And so now, in order to move this circle around with this XY, we need to incorporate this ring position somewhere. The place we're going to do it is actually up here. We can't do it right here because we've already turned it into a pattern. So we need to do it while we're still working in the XY landscape. And so that's up here, ring position. Is that what I called it? Yep. So let's just add that in. And look at what happens. Okay. So we have the ability to move it. It's a little weird though. It's going in reverse. That's because we actually need to subtract instead of add. Okay. And now it's right, but it's not giving us the full, like, I can only move it back to the center, right? I can move it up and to the right, but I can't move it down and to the left at all. Well, that's because the bounds for this XY are out of position. So you can adjust those right here in the config, open up ring position, and you'll see right here it has min, max, and default. So for the min, let's put in -1 and -1 for Y as well. And now I have full ability to move it, right? Oh yeah, and by the way that, so by the way, this is also super useful to know. Controls all have defaults, right? So if you click default, it will return every control to its defaults. Unfortunately, right here, if the default for both of these is 0, you don't see anything, right? So that's actually not a very good default for these controls. So for ring thickness, let's add a default value real quick of 0.2. And for ring radius, let's add one as well, make it 0.2. Now hit default. Okay, cool. And maybe that's kind of too fat of a donut. Let's do 0.05 and 0.5. Okay, cool. There we go. Okay, so final thing looking at these controls, let's say you're like, that's, it's kind of cool. I can move it around, but it's also kind of like jerky, It's not really something I would want to put up on screen at a show. Same with the radius. It's just kind of like, it could be cool. I could be like really careful with my mouse. But instead of doing that, you can just change these controls by adding a modifier to them. So put a smooth modifier on them. And then let's actually put a smooth modifier on all of them. And then save. So now if I move it around, it's a lot more, it's a lot smoother. And it looks pretty dang cool, actually. So in general, I would recommend using smooth controls almost anytime you can, because it'll just make your visuals look juicier. So, and one thing about this down here, so as soon as I add that smooth modifier, you see I've got this slider to control how fast I want it to update. right? So this is like much more responsive. If I turn it way down here and save. Okay, so we have our circle. What if we wanted to squish it and make it into an oval? Well, if you were working in Photoshop, you might think, okay, first I'll make a circle. Now I'll do a transform on it and squish it down. And then I'll end up with my oval. So when working with shaders, you have to invert that logic. What you want to do is always transform space and then generate your pattern. So we've got our position and center pause here. The center pause is being used to generate the distance. What if we took center pause and multiplied it by a vec2? And if we just do it by 1, 1, nothing will happen, right? What if we did 2? Okay, so we made that actually is interesting because it made it taller, not wider, right? Because we're doing the inverse of whatever transform we're asking for. So you might think, oh, well, because you multiplied x by 2, it should make x twice as big, right? But it's the opposite because we're transforming space and then drawing a circle. So yeah, check this out. Color out equals vec3, center pause, 0. So you can see what we actually did when we multiplied x by 2. It makes x max out right here. And everything after that, x is already 1.0. It also maxes out negative, although we can't see that here, right? Because you can't go any darker than black. If we multiplied the y value by like 3, right, you can see, okay, now that maxes out right here. So what's our circle going to look like? It's going to look like that. And if we did 10, it'll look like that, right? This is one of the things about shaders that's kind of like mind-bending, but extremely powerful. Because once you transform space in all this way, in some fancy way, you can draw a circle and have it be so much more than just a circle. Now I want to look at animating things, so making them change in time. And to do that, you've got to introduce the time variable. So this is another built-in variable, just like UV and UVC. So check out, so let's draw this down here. Let's just say color out equals vec3 time. And you don't have to type this. I'm just going to show you something. Okay, so anytime I refresh, time is going to start at 0, and then it ticks up with how long the shader's been running. So after a second, it's at 1, and it's just going to be white forever now until I restart the shader and it goes back to 0, right? So how can we use this in a more interesting way? Well, there's our old friends from trigonometry, the sine function. And sine goes up and down over time. And so now we have something that's animating, it's oscillating up and down. Sine goes from -1 to 1. So if we wanted to keep it between 0 and 1, instead of going all the way negative to -1, we could do 0.5 plus 0.5 times sine. And that just recenters it, renormalizes it between 0 and 1. And then what if we wanted to oscillate faster? Well, we can just multiply time and do a transform on the space that time's in, basically. Scrunch that number line down or stretch that number line out by multiplying by 0.1. Okay, now it's going to go super slow. What if we multiply by 5? Okay, sweet. Okay, we're back to our circle. Now I'm going to introduce 2 new concepts, and that's noise functions and polar coordinates. So let's do noise functions first. A noise function is something that generates, well, I'll show you first. So let's make a new variable called noise val, FBM, vec3, UVC, and time. Okay. We're going to come back to this, but for now, just type that in, and I'm going to show you guys what this looks like. Noise val. Okay, so noise is used to add some randomness and make things look more realistic when you're doing computer graphics. And so we're going to use it to animate in sort of a random wavy way our circle here. So to do that, let's get rid of this. And we're going to do center pause plus equals noise val. Okay, starting to look a little more interesting. It's pushing everything down to the left, and I don't like that. And that's because this noise val is actually all centered around 0.5 right now. So if I do the same trick I did with sine, but a little bit different, I'm just going to subtract 0.5 first and then multiply by 2. And so now it's centered around 0. So it should be pushing things up just as much as it pulls them down. Let's see if that worked by getting rid of that. It's centered. So it's pulling it up and pushing it down equivalently. And if we want that to just be a subtle effect, just multiply it by 0.1. Okay, so we've got this animated using FBM. Got a little noise function in there. And I'm going to actually turn this off for now. We're going to look at another way to animate using another coordinate space called polar coordinates. So let's bring that back there. And let's look at this. So I'm going to make a new vec2 and call this polar pause. And for this, we're going to use the built-in function toPolarTrue. And let's just put UVC in there. And so this takes those normal centered coordinates and turns them into polar coordinates. And you might be wondering what those look like. Let's take a look. So again, I'm just going to visualize this. Okay, so if we look at just the red, this goes from 0 in the center and it goes out. So this is kind of like radius. And in fact, it is exactly radius. It's the same as length of center pause, length of UVC. And if we look at the Y value, that, and I'll put this actually over in the green just for consistency, that is going from 0 here, and then it actually changes based on angle, like the angle around the circle that you're rotated. And then it goes from 1 and cuts back over to 0. So looking at those two together, cool. So the one we're actually interested in using here, because we already kind of had that red channel, right, is this green channel. So this allows us to now define what part of the screen you're on based on angle. And so let's use that. So we have here this circle. If I want to define just a segment of this circle, I could say float segment equals pulse. So we're going to use that pulse function again to make something that goes up and then down. But we're going to pulse around that Y value of polar position. Polar pause dot Y. And let's put the pulse right here. That's not going to do anything yet. Let's look at, let's do this. Okay, cool. So that's what that looks like if we put it at 0.2. It's up there now. Put it at 0.8. It's down there. And what if we multiplied this pattern by the circle pattern, right? So this is that pattern. This is the segment pattern. Let's multiply the two together. Segment equals segment times circle. typing. Sweet. This makes sense, right? We're just basically multiplying those two together. Where one of them is 0, you're going to get nothing. Now, what if we want to rotate this? Well, we could just do time here. And that works until time goes beyond 1.0. It's never going to come back, right? So we could use this function fract, which is another awesome function you're going to use all the time. This takes just the point after the decimal place, right? So if it's like 10.5 and you do fract on it, it's just going to give you 0.5. If it's 2.6 and you do fract, it's going to be 0.6. So this is good, except there's this seam. You guys see that? And we don't like that seam because it's ugly. So what we're kind of doing here is we have our polar position, and then we're drawing a pattern at different spots along this, but that seam is the problem. So we know that the pattern looks good if we just put it at 0.5. So instead of moving where we're drawing that pattern, why don't we use what we know is the better way to do things in Shaderland? Let's transform the coordinate space and then draw our shape. So to do that, let's change polar pause. And if we want, we can call it something new, like vec2 rotating polar pause. Say it equals a vec2. We're going to say polar pause dot x. Leave that one alone. We just need to worry about the second one, polar pause dot y. But let's add time to it and see what that gives us. Okay, so that looks like it could maybe work, but it just caps out, right? Once again, it goes over infinity, or it goes over 1.0, and it's just going to keep counting off to infinity, never to return. So let's put that in a fract. Sweet. Okay, we have rotating coordinate system. Now, let's see what happens here. Putting rotating polar pause in right here. Yes. Okay. So, hammering that point home because it's going to come up in your shader journey all the time. You're going to have an idea. You're going to be like, I want this to be rotating. Just remember, rotate your coordinates, not your shapes. Awesome. Okay, so we have that. What if we want to slow it down a bit? That's going a little bit zany. That's too much. Let's do like that. Sweet. All right. Okay, so we have this segment. I'm going to change the shape of this segment a little bit. I want it to be a little bit skinnier. And actually, I think I want this to be a segment with hard edges instead of soft edges, just to make it a little more clear what's going on for now. So we can just swap this out from pulse to underscore SQ pulse, which is square pulse. Okay, so we have one of these. Let's make 8 of them. There's multiple ways you could do this. You could change space and draw one of them, right? In the same way that we did before. And so actually, it's kind of crazy, but I think I could just multiply this by 8. Boom, right? So that's kind of cool. That's, again, showing the power of changing your coordinate space and then just drawing your shape as normal. But we're going to actually do it the other way. So OpenGL GLSL does have for loops, just like, Python and C. And so we're going to do this in a for loop because I want a little more individual control, right? If I had, I could make 8 of them, but then if I make any change to one of them, I change all of them. And so doing it in a for loop is going to give us a little bit more control. So I'm going to write a for loop here. For int I equals 0, I less than 8, because we want to run it 8 times, I plus plus. Every loop, we're going to increase I by 1. Let's put segment in here now. And get rid of this. Now it's going to complain because segment is not defined. So we're ahead of this for loop. We're going to actually make a new thing called segment colors. And this is going to be an empty color. This is going to be a vec3. It's going to just be holding black for now. And then down here, instead of adding segment to color out, let's add segment colors. So this makes sense. There's nothing happening yet. Segment colors plus equals segment times vec3 1.0 0.0 0.0. Okay. So this is adding this red segment in, and it's actually adding it 8 times. And there's no difference yet between them because we haven't used the I variable yet. So what if we change where these are centered based on I? Let's actually bring this thing into, I thought I wouldn't need this, but now I want it in here as well. Let's bring this inside the loop, and let's add I to this. And I is going to go, it's going to be 1, then it's going to be 2, then it's going to be 3. So just like this, it won't change anything, because fract will get rid of those components anyway. But if we divide by 8, sweet. Now we have 8 segments, and we can actually make them do different things based on which I they are. So instead of just making these all red, and you know what, for now, I'm going to get rid of this teal orange background. It's served us well, but I think we can make some more interesting color things happen. So I'm going to say color out equals vec3 0. So once again, we're starting with black, and we're adding these segment colors. Okay, so let's change the color based on I. So we could put I divided by 8 here as well. We can also use more interesting coloring functions, like, for instance, this one, HSV to RGB. And this takes a vec3, takes an RGB color, and will convert your red channel into the hue, your green channel into the saturation, and your blue channel into the value or brightness. So HSV color space is like an alternate color space from RGB. So you can go HSV to RGB to convert the colors. So let's do I divided by 8 here. And then for the saturation, I want it fully saturated and full brightness. Sweet. We have rainbow. Maybe we want to be a little smart about this, and instead of just having this 8 appear in all these places, maybe we want to make this its own variable. So we'll call this num segment, and I'm going to start with that at 8, and we'll put num segments right here, and right here. And now if I change num segments like to 18, okay, cool, that's what 18 looks like. That's what 4 looks like. Sweet. Do 10 for now. So obviously one of the most important things about synesthesia is audio reactivity. So let's make this audio reactive. How do we do that? Well, I'll show you guys in the SSF docs. If you click up here again, you can go to SSF audio uniforms. This will tell you everything that synesthesia is providing. And these are variables that you can just drop right into the GLSL. Your level is basically like your volume. Your hits are going to be picking up really quick action in that part of the spectrum. And then your presents are going to be ones that very smoothly rise and fall over time. So these are always being processed in the background. And this is how synesthesia animates scenes automatically, is that the creative coder has just put these variables in certain spots. So let's do something based on the syn_base level, and we'll take the hits, which are a little faster. We'll use the syn high hits, and we'll come back to check out some more after. right here for the brightness, instead of 1.0, instead of constant brightness, let's just see what Syn high hits does. Cool. Okay, so we have that flashing on high hits. What if we bring in the bass as kind of a background color? So let's do color out plus equals. I'm just going to add in another color right here. Let's do like a kind of a warm reddish, orangish, and multiply that by Syn base level. Okay. And then instead of happening over the whole thing, because that's a little much, what if we multiply this by our classic length UVC? Cool. So this is a little bit, it's good, but I actually want the center to be more black because it's kind of crowding this a little bit. I want to push that out towards the edge. So I'm going to use what I would call a shaping function to manipulate the curve on this. If we were just doing X, right, this is just an unshaped curve, and you can use POW to shape this curve in different ways. So if you want it to spend more time towards 0 before it crosses 0.5, then increase this number, right? Okay, so that's 34, that's 3, that's 4, that's 5, right? And you can go in reverse too. So if you go 0.5, now it's going to spend more time above the middle and only get to 0 right towards the end. So using POW with a fractional power here or an integer power can let you shape your curves nicely. I'm going to apply POW to this length function, and yeah, maybe I'll even put it up at like 5. Cool. Okay, sweet. So you can see how that left the center so much more open for us to play with. Maybe we can even multiply by noise val. Bring that back in. So now it's kind of got this like cloudy effect along the sides. I think that works. Let's add some more audio reactivity because these guys just circling, they are begging to be animated. So let's check out another variable here, audio uniforms. About these ones, these beat uniforms. So Syn random on beat is a pretty awesome one. That's going to choose a new value in between the range 0 to 1 whenever a beat is detected. Let's put that in right here. Now, whenever there's a beat in the music, it's going to be randomly separating or bringing these together. And so I'll let you guys hear the music for a sec. See how that's working. And I've still got these down here, right? I can still control. Okay, cool. And if you don't want it to go like, all the way flashing from 0 to fully on the high hits, you can just do something like 0.5 plus 0.5 times Syn high hits. And so now, even if I pause my music, it's not like they disappear fully, right? So now let's add something using the BPM variables. And these are actually going to use Synesthesia's automatic BPM detector, which, if you play crazy music into it, it'll do its best to try to figure out the BPM. But usually with electronic music or, any sort of consistent BPM music, it'll detect the BPM and then it'll start an oscillator that moves along at that same BPM. So let's actually do something that's highlighting along this circle variable. So I'm going to call this highlight, and we'll do a pulse on the circle variable, which if you remember was 0, and then right in this area where those shapes are, it goes up to 1, and then it goes back to 0. So we're going to pulse along that circle, and we're going to do 0.1, 0.1. And then let's add this highlight in at the end. Color out plus equals highlight. Cool. And now let's add in this BPM variable here. So something like syn BPM sine 4. See what that does. Cool. Okay, so now it's oscillating with the BPM of the music. And if I want to make it so it doesn't completely white out the scene, I mean, maybe you like that, but I'm going to add this so it doesn't fully reach 0 where it was whiting out. And actually, I think I don't want it to like fully disappear there. So let's multiply this by like 0.4 or something. So it's just going back and forth, giving it a little extra motion, a little extra synced action. All right, let's throw some media in there. So to add media, we will make a new color down here called media, and we'll do load media dot RGB. So this is a function that will bring in whatever color your chosen media down here has. And make sure you get the .rgb because we want to work with a VEC3 version, just RGB. We don't need the alpha channel. So if you miss that .rgb, it'll yell at you. And then let's say color out plus equals media. Sweet. So now we've got the video playing and it's actually added into our scene, right? And it can be static images, it can be videos, whatever you have in this folder will show up in the back here. So we've got that color added in. It's kind of a lot going on. What happens if we multiply? Okay, so now you can see when the video has color and it lines up with the color of the scene, we multiply together. If you've used Photoshop before, you may recognize this as the multiply blend mode. The reason it's called that is because it's multiply. The add blend mode is add. The divide blend mode is divide. And that's going to give you all sorts of glitchy stuff. A lot of these things that you may be familiar with in other sorts of image processing apps or like workflows are really just shaders under the hood. So there's a reason that that's called multiply. So this is kind of cool, but I would prefer if there was more going on. It's too dark, and I think I don't want to multiply everything in the scene together into one thing. That's kind of wasteful. Let's make a new ring and multiply that by media. I'm actually going to change this circle. We know that this is actually a ring now. It's not a circle. So I'm going to change that there and here as well. And here as well. So now I'm going to make a second ring. And for this one's going to be just for media. So down here, I'm going to make another thing. It's going to be called maybe media ring. How about that? And let's make a media ring highlight as well. That'll be the same thing as we had up there, except it'll be acting on media ring. Now let's add these together. So media ring plus equals media ring highlight. And now, instead of multiplying color out by media, I'm going to change this back to add. But now we're going to multiply media by media ring. Cool. All right, we're getting somewhere for sure. What if I want this to be kind of the inverse? So instead of coloring up the same place those segments are, it's coloring everything else. That's almost cool. But still a little intense. Instead, I think I'll just offset by changing this radius a bit. So it's got its own ring now. In the interest of moving things along, I'm going to call that cool. And let's move along. So the next thing to add into the mix is going to be a little crazy too, because we're going to jump right from media into feedback. You're probably familiar with feedback from the audio world. If you have a mic, you hold it in front of the speaker, comes out of the speaker, goes into the mic, get a terrible sound. Video feedback is actually a lot cooler if you've ever played with it, where you're pointing a camera at a screen that's showing what that camera's feeding. And you get this very interesting kind of tunnel effect. Well, you can play with that in Shaderland too. So in order to do that, we need a back buffer to be rendering onto. And then the shader can look at that kind of virtual back buffer screen in order to set up the video feedback. So to do that, come down to render passes. And this is how we make a multi-pass shader that can have multiple steps of rendering before it comes out on the final screen. So click the plus sign to add a buffer, and it's going to be named buffer to start with. We can just stick with that name, that's fine. Leave everything as is, except turn double buffering to on. That's always a safe bet. If we're going to be doing some video feedback, you're going to want double buffering on. So now, there's actually going to be two whole passes here, and this will be kind of interesting to set up. So everything we're doing here is going to happen in the first pass. So if pass index equals 0, we'll take everything in here, press tab to indent it, and wrap that entire thing in this if statement. Now, if you save that and try to run it, you're going to get a black screen. The reason is because now there's a whole second pass. So else if pass index equals 1, return vec4 1 0 0 1. Okay. So this is showing you that what actually ends up being shown on the screen is whatever's in pass index 1. And whatever is in pass index 0 doesn't matter right now. Except what we can do is say vec4 last pass equals texture buffer UV. And so this texture function is going to look up whatever pixel color we have in buffer at this coordinate, UV, which, as we know, is the normal XY lookup. So now let's view what last pass looks like here. Boom. It's what was rendered in that first pass. And this is kind of interesting because, so even before we get into feedback, this already lets us do some cool stuff. So if we, for instance, wanted to just, let's just say we want to vertically scroll this, right? Like a film reel or something. We could do that by transforming all of space up here, right? And then making it so every single shape that we render afterwards is being transformed by this Y value scrolling. Or we could say, hey, we already rendered the image, that's saved. Let's just offset where we look up that image in order to do the scrolling. So instead of looking up this image at UV, what if we look it up at UV plus vec2 0 time? This will give you a good idea of what this texture looks like, actually. What if we did UV times vec2 2 2? When you introduce multipass rendering, now you can think of it sort of in the way that you'd think of it in Photoshop, right? Okay, now that I have that circle, I want to squish it. Well, you can do that here, right? So that's some of the power of multipass right there. And yeah, it also opens up other effects like edge detect or blur, right, or bloom. Let's get to feedback. The way you do feedback is by adding in this buffer to this pass. And if you wanted, you could do this without this like pass index you would just be running this code twice, but it's actually making the GPU do a lot of unnecessary work. So we're going to be nice to the GPU. We're leaving this else if pass index 1, then do this really simple thing. In order to get this feedback running, we want last frame to be present in pass index 0. So to do that, we're going to do the same thing we did below. We'll call this last frame equals texture, buffer, UV. Let's now put in accessing the last frame in this frame. So to do that, we're going to bring that back in. We're going to say vec3 last frame equals texture, buffer, UV dot RGB. And so once again, this is saying, look at what I rendered to buffer, pull it up, and bring it into this frame as this variable called last frame. Where are we going to look it up? We're going to look it up at UV, just the normal spot where it normally would sit. Now let's do color out plus equals last frame. Okay, something's definitely happening. You can see that it's actually kind of maxing out the colors. So now we're not getting any action in the ring. If I restart again, you can see it takes a sec to kind of max out. This makes sense because we're just adding to it. We're never subtracting from it. What if we do times 0.9? Okay. So now you can see it's not maxing out as much, right? Because we're not just adding infinitely. It's naturally decreasing how much last frame is going to add in. And so if you really want to see this effect more, we can bring in the idea of offsetting our lookup. So instead of just looking up at UV, because that's kind of boring, let's say we're going to have an offset. And offset is going to start at UV. Put offset in instead of UV and run that. Should look the same. Now, what if we do offset plus equals vec2? We're just going to add a little bit to the y value. Okay. So now you can see what's happening with a little bit of offset here. Basically, each pass is looking up just a little bit higher than the last. And that has the inverse effect of moving everything down. And then because we're doing this times 0.9, if we got rid of this again, you'll see it max out pretty quick, right? But we want it to not just infinitely loop. So that 0.9 is really nice. And if you go 0.5, you see you get really short trails, right? Which could be kind of cool effect too. Let's go for like maybe a 0.8 for now. Kind of a middle ground. Okay. And what if we wanted to animate that a bit? Instead of just coming down, what if we did sin base time times 0.1? Okay. Cool. Maybe a little intense. So let's multiply that whole sine times like 0.1, 0.01. Okay. Yep. So that's a little better. And maybe we can just do time, depending on your music. You know, you can drop in whatever variable you'd like to drop in there. Kind of depends on what genre of music you're working with. So I think my music's pretty constant here. I'll pick some music that's a little bit, got some more dynamics to it. This one. So yeah, now you can see that when the audio level picks up, it is doing more of the feedback effect. And when the level's low, the offset is less, right? So that is fun, but I want to control this feedback more. So let's add some new controls. And I went ahead and deleted that green amount slider since we're not using that anymore. Here, let's first make a knob called FB rotate. This is going to go into the feedback group. So let's make a new group called feedback. And let's make this a knob that can go from -1 to 1. Save. Okay, there's our knob. Let's add another. This one is going to be called FB amount. And let's make this a knob as well. And this one's going to be controlling this right here. So we actually just want it to go from 0.5 to 1.0, let's say. And let's default it at 0.8, since we're going to drop it in right here. And let's save that. And let's make another one. This is going to be worth it, trust me. This one's going to be called FB offset. Add that to feedback. We're going to make this go from -1 to 1 on both axes, the X and Y. Make it smooth. And let's add one more. This will be called FB zoom feedback. Let's make this a slider is fine. And let's make it smooth too. And this one goes from -1 to 1. So, got that all out of the way. I'll make these other ones just smooth too. So everything is smooth. So we get that juicy feedback. And now let's drop these in. So FB amount. Well, actually, we'll do this from top to bottom. So first, offset plus equals UVC times FB zoom. So this is how you add a sort of tunnel or zoom effect to the feedback. That's going to be really nice. And you maybe notice that it's like the tunnel's a little bit stretched right now, right? It's kind of an oval. That's because feedback is a screen space effect. And we're using UVC because it's important for the zoom here to make the tunnel effect, but it's going to be stretched as a screen space effect. So this is probably going to be over your head right now, but just trust me, go with it. We're going to rescale this a little bit by render size y over render size.x. And so now it's going to be circular, and it'll be circular even if we change the aspect ratio of this. That's the nice thing about dropping render size in as a variable, because this is basically just the render size of the final pass. So we have our feedback zoom working. Now we want to add our rotate. So for that, we'll do offset equals rotate offset by FB rotate. And this will work, but it's not rotating about the center, and it could look way cooler if it's rotating about the center. So we have to do this kind of weird thing where we are going to offset the offset by 0.5, and then we're going to rotate it, and then we're going to correct what we just did. We're going to do the inverse of that. Tract, then do the rotation, then add it. And you can see that is rotating about the center. It's still squashed, so I want to fix that now, but that's a lot better. So now to fix the squash, let's do offset times equals vec2 render size dot x over render size dot y. And then right here, we're going to do the inverse of that. So offset divided by equals vec2 render size dot x over render size dot y 1.0. There we go. All right, so there we go. Now we have a juicy feedback zoom and a juicy feedback rotate. Let's throw in this little feedback offset, and that's nice and easy. So that's just offset plus equals FB offset. Probably want to scale it, so like times 0.1. And yeah. And if you want, you can make that a subtract so that it's a little more intuitive. Like, if I push this up, I want the trails to go up. If I pull it down, I want them to go down. So cool. And you could even scale that a little lighter if you want, like 0.5 to be a little more delicate on the feedback. Okay, so the last thing is the feedback amount. So down here, put FB amount. And I think now we have a fully controllable system. So if we want to turn up that FB amount to like max, you might want to make it so FB amount, the max can't actually go to 1.0, because if you go up to 1.0, you're just going to fill everything with white, right? Before too long. So maybe make that max out at like 0.99. Now that we've got feedback zooming, let's actually try to change the amount that the feedback will happen, basically, based on the media. So I often like to work, since media comes in with all kinds of colors, and it can just be difficult to work with 3 different colors. Sometimes you just want to work with it in black and white. So first, let's convert media to black and white. Let's save a copy of it. Float media loom equals media.r plus media.g plus media.b. And then let's take that whole thing and divide by 3. So we're basically taking the average of these 3 color channels, and we're calling that the media luminance. So now we're going to use this media loom in a cool way. Down here, we've got the offset, and that is basically where we're looking up this is like the offset position, right? What if we said offset is actually going to be equal to mix between UV and offset? And just to show you what happens if we put a 0 in here, now we're not doing any offset, right? So it doesn't matter what rotate, zoom, what anything is set to. And if we do 1, it's going to be the all offset, right? Let's put media loom in here. So now where media is bright, we're offsetting, and where the media is dark, we're not offsetting. And so this is giving us a much more dynamic feedback effect now. And it's really going to change based on which media you choose as well. Awesome. So I'm pretty happy with how this shader turned out. Okay, so I know what you're thinking. Sure, the 2D feedback stuff, it's super cool, but how the heck are we doing 3D stuff like this, like this, like this? How are we doing 3D stuff in a world that seems like it's mostly 2D, right? We're starting with X, Y coordinates. So to explain this, I'm actually going to take a step back and let's look at what the typical graphics pipeline is for video games. I kind of hinted at this earlier, but there's actually different kinds of shaders. So we've only been looking at pixel shaders today, also called fragment shaders. Same thing. The next most common shader is called the vertex shader. And actually, that comes earlier in the pipeline, in the like 3D pipeline. So a typical game engine, 3D game, if you've played any 3D video games in the past 20 years, it's used this, where you go vertex shader into fragment shader. And the vertex shader takes in these points, you make them into triangles, you rasterize them, which means figure out how many pixels are going to be in each one. Then you tell the pixel shader, run on these pixels in particular, and not just the whole screen. So the vertex shader is kind of like this right here, right? And the fragment shader is over here. And this is obviously not like a very complex fragment shader. We could make it look probably cooler than that, but that's a nice like stylized fragment shader. So you can kind of think of it like that though. Like the vertex shader's job is to take a bunch of points, turn them into these gray triangles. Then the fragment shader's job is to paint those. And once you're in fragment shader land, you don't know anything about 3D anymore because the fragment shader is operating on each of these surfaces as just a flat plane. So if I go to Shader Toy here and we look at, yeah, I don't know, this one. Obviously, it's 2D. It's operating on a flat plane. How the heck are they doing these 3D ones? So it's actually kind of more insane than you think because here's what we do with the vertex shader. And this is just from a talk that E.K. Lesles gave. He's the guy, IQ, who's like one of the best 3D artists in Raymarching. He is the best. He's definitely the best. He is the best 3D artist in terms of Raymarching. It's ridiculous. So he made this entirely in 2D. And what I mean by that is he doesn't have a 3D mesh. He doesn't have this 3D object that he imported. He had to sculpt this out of math and then write his own render engine inside the 2D shader to get this to look 3D. So this is how that works. I'm just going to give this brief overview. The vertex shader is actually only these two triangles. And then you put the camera right in front of those two triangles. So it's basically, imagine setting up a 3D scene where there's a billboard, and then you put the camera right in front of the billboard. And then the fragment shader's job is to paint the billboard, right? So that's actually how all of Synesthesia runs. It technically does have a vertex shader. It's just, there's two triangles right here, and the camera is looking at those two triangles, and we're painting the billboard in a really fancy way, right? So that's this kind of style of rendering where you just throw away the vertex shader. So I was explaining, we've thrown away the vertex shader, right? Now we're just in 2D land, yet we can render 3D scenes. How is that possible? Well, you have to use a special technique called Raymarching. And the way this works is you basically set up your own render engine inside the fragment shader only. You set up your own 3D render engine. So basically, you start from a point, the origin, and you project rays out in 3D, and they are going to hit some objects that you've defined. And you can't just import a 3D mesh because, a 3D mesh of triangles like you'd have in a video game. You can't just import one into a fragment shader. That's the vertex shader's job. That's the earlier in the pipeline, right? So fragment shader has no idea. It can't work with triangles in 3D space. So instead, you need to define some 3D objects. And in order to do that, you use these things called SDFs. And so this is this guy, Inigo Quiles, IQ. He is an absolute wizard at making these 3D scenes. All of these are his. He also wrote these articles that are mostly a lot about this kind of rendering, this 3D style of rendering. So if you read through these, you will learn a lot about all kinds of awesome techniques. Some of the most advanced stuff. He's incredible. But the key one here is this 3D SDFs article. These are basically your primitive objects. So these are the different shapes that you can use, and this is the math that defines them. So if I want to put a sphere in my scene, I can copy paste this into my scene, and then choose where I want that sphere, what size I want it, or a box, or a torus, right? So there's all these different shapes you can use. So that's how you define your shapes. How do you see your shapes? That's through the Raymarching. So imagine that he's defined these shapes with math. They're out there, but the question is, what ray hits what shape? So to answer that, we're going to use Raymarching. And so that's where we have this ray, and we're going to ask a question. What is the minimum distance to one of these objects, any of them? And it returns, because these are signed distance functions, SDFs. The whole idea is they can tell you how far away from the surface of the object you are. So you get the answer back and you say, okay, great, I'm going to march that far forward. And I know that's safe because that is the minimum distance before I hit an object. So I'm sure that I won't hit an object if I only march that far. Then you ask the question again. And now it says, oh, well, now actually, this is how far from an object you are. So now I'll march that far. And I'm going to ask the question again. Oh, well, now this is the minimum distance. So you are safe to march that far. Ask the question again. Now it's this. So I'm safe to march that far. And so on and so forth until you hit the object. And at that point, the distance between you and the surface is getting smaller and smaller with each march, right? Until you hit some minimum and you're like, okay, just cut it off there. Let's say that we hit the surface now. So we marched this ray forward. That's Raymarching. This is happening not just in 2D, but in 3D. So let me show you this demo that someone made. Pretty awesome. They explain Raymarching by making a Raymarcher. So this is your camera point. You project rays out through your render screen. This is choosing the field of view of the camera. That's basically your projection matrix for the camera. There's your first step. There's your second step, third step, fourth step, fifth step. And so and then we hit, right? So now that's happening per pixel on the screen. And that's your final image. So that was kind of fast, but it's a pretty cool way to visualize what's going on here. Okay. So this is the actual marching. And this is the rendering. So every ray through each pixel gets a different angle, right? Or a ray direction. So, and then this, once more, is the final render. So let's look at a Raymarcher in Synesthesia. And there's actually one included in the folder that you downloaded and already added. So find the scene 3D tunnel cam template. Let's start that one. And actually, let's edit that one. And hop over to the Edit tab. I'll switch back up here. Cool. So this is our 3D scene. And real quick, I'm going to just show you everything that's already baked in here. So this is the 3D scene with 3D lighting. And we've got the ability to move the camera around. You can see that it's actually 3D. And there's not not too much complex going on, but we have some shapes, we have some camera controls, and we have the ability to change the texture that it's colored with, the coloring function for it, basically. I'm going to break down this super basic Raymarcher for us, and then we'll make a couple little tweaks to it, turn it into something slightly cooler, and the world of Raymarching is so deep, so we can't go that deep on this today, but this will be a good scratching the surface of it. This is a template Raymarcher that Kyle or Oof put together, and it's very well commented. So you can actually learn a lot just reading the comments here. But I'm gonna walk us through a little bit, and we'll just try to understand this function by function, basically. So at the top here, we have our shape functions. These are exactly what I was just telling you about, the SDFs, right? So you can see we copied the box and sphere, and that's what we're working with here. We've got the function for a box, function for a sphere, nothing special there. We just copied those over. Next is the map function. This is like the most important function in any Raymarcher because this is what defines the actual shape of the scene. This is basically where you sculpt your scene. So here we are taking in our position, and first we're saying, let's make a sphere, create a sphere, and then we're saying D is our distance, because what map is doing is it's going to basically be combining multiple distance functions into one, and then returning the distance to the shape, which is the combination of all the shapes we've made, right? So so here we have the first sphere. Let's just make that like 0.2 and see what happens. Right. We can move the sphere around in space by just messing with that variable. Cool. And this one is probably going to be the radius. Yep. Big sphere, little sphere. Wonderful. Now we've got the box. Same situation. If you add or subtract right here next to position, you're going to be moving the shape around. And here is the parameters for the box. If I want to make it bigger in one axis, I can add a 0.5 there, or make it skinny on that axis. Pretty straightforward, actually. And here's the first kind of cool thing. So how do we combine these different distance functions? We do it by using min. And that's also right here. He actually explains down here at the bottom that you can do lots of fancy things, but here's the simple stuff. If you want to do op union, which is basically union operator, it's just adding the two shapes together, then you just do min of the shape 1 and shape 2. So that's what we're doing here. We're just doing min in order to combine them. If you want to subtract them, you just do max. Like here, he's doing max max of the negative of 1. And so you can see that's what we're doing here. Max of the negative of the sphere subtracts the second sphere, which is defined right here. If I want to make that bigger, you can see, okay, now we're subtracting a bigger sphere from them, right? And then finally, we're adding in this tunnel, and that's going to be kind of simple here. It's actually just defined by how far away you are on XY. And if we want to just take that out, we can comment that out, right? So this is our tunnel. Here's where we get the normal. We're going to come back to that because we are going to use that later. And now we get into the marching. So we defined our shapes in map. Now we're going to march out to find those shapes. Here's how we do it. We're going to set up some variables. And what we're taking in here in the Raymarcher is this RO, which is our ray origin, and RD, which is our ray distance. Usually people will use these same variable names. So if you see RO and RD, like it's probably doing some Raymarching. They're super common. So, and actually we can see where we get those down here. So we'll just take a little detour down here and say ray origin is going to be starting. It's going to be starting just at 0, 0. But in this case, since we have those camera controls, that's what you see there. And then the ray direction is basically taking from that point 0, 0, 0 and projecting rays out, 1 ray per pixel, right? And so in order to project those rays out into 3D space, we're going to use UVC. And this kind of defines the direction we're projecting them. So if I do negative there, now the camera's facing backwards. And if I do positive, it's facing forwards. If I change this to like 0.1, it changes the camera field of view, actually, right? So that was kind of that animation where the dot is getting closer or further from the screen. And 2 is going to be a much more narrow field of view. Let's keep it at 1.0 for now. Cool, so that sets up the camera, actually. And then we've got the rotate that just is doing some simple rotations. Nothing too fancy there. So ray origin, ray direction are what we're passing in here. Now, all of this doesn't really matter. The key point here is the for loop, where we're saying P, our position, is going to be ray origin plus RD times D. And D is going to be the distance that we've stepped so far. So how far should we step? Get that here. This step is going to be map, right? Map is the thing that whose job it is to return the minimum distance. That's why we're using min to add these, the minimum distance of these shapes. And that gets returned right here. So we're going to add that to D. So D is just a running total of our distance that we've stepped. And we're going to do this in this for loop, and we're going to be stepping through. And then if our distance to step, which we get from map, right? If map ever returns a value less than 0.001, then we say, hey, we hit. And then we call break, which breaks us out of the for loop and immediately jumps to here. Right? So we're going to step, how many steps? We can actually step up to 100. And the max distance we can step away from the camera is going to be 10 units. So there's 3 ways out of this for loop. Either we take 100 steps, we go 10 units away from the camera, or we hit an object. And hit is going to be defined by being less than 0.001. And I'm going to take this tunnel out for one moment. And so what happens once we hit our surfaces? Well, what we're left with is actually something that looks like this. So we have now a 3D space, and we can, the kind of most simple visualization for that is to look at how many steps did it take to hit our object. And so this is the depth, and you can see this banding. It's actually kind of a classic Raymarch look that you're usually trying to get rid of. But this is like visualizing how many marches it took to hit the object. And so the places that are darker here, let me invert that actually. So the places that are brighter here are actually the things that took the most steps to reach. And it's kind of interesting, but like when you get close to a surface but you don't hit, the distance that you're allowed to march gets super small. So that adds up steps a lot faster. Yeah, there you go. You can see it right there, right? As we come right over that, the top of that cube, it gets pretty bright. All right, so in the world of Raymarching, I'm going to teach you 2 little tricks that are pretty fun and just kind of show you the power of working in this world where you're not using a 3D mesh and we're working with SDF. So once again, we can apply this kind of logic of like, if we want to draw infinite objects, what if we transform space itself, and then just draw one object. So we're going to do that. And we're going to use, you could use mod, or we're going to use our old friend fract to just duplicate space. Every time it counts up above 1, it's like going back to 0. And so we're going to make this variable prep, which is kind of repeated position. And just swap out every one of these p's with prep. And boom. We now have infinite objects. You can keep scrolling literally to infinity, and you will continue seeing objects. You'll eventually run into like, floating point limit. But that's pretty cool, right? If you wanted infinite objects in a normal game engine, it would cost you per object that you're adding. This is pretty much exactly the same. This is within like, probably 1 or 2% the same amount of rendering that it takes to render a single object. In some cases, it's actually even cheaper to do multiple objects rather than one, because Raymarching is weird. So that's pretty sweet. And what happens if we do this on the other axes too? Because right now we're just duplicating the z-axis, as you can see. What happens if we do x and y? And then right here, we'll make that x and make that y. Boom! We got infinite objects in all directions. So if you've been following digital art in the past, like, I don't know, or computer graphics at all, in the past 10 years, you've probably seen stuff like this, where it looks like infinite objects, and you're just like, what the heck am I looking at? That looks a little different than like a normal game engine kind of setup. It's Raymarching, and that's a pretty cool thing you can do. If you look over here, you'll see this is like kind of broken. Also, weird stuff happens when you like intersect with the objects. So Raymarching, powerful, but you have to tame it. There's these weird little quirks where you can break it if you're not careful. So that's broken because that's like the seam between these objects is happening right in the middle of our box. And so the Raymarcher doesn't have it's not a well-defined distance function right there. So infinite objects, let's talk about coloring the objects a little bit. So Kyle added these cool color modes. So depth map, this one's kind of the most simple just based on the number of steps you've taken. This grid is awesome. This is this one-liner here, which it's kind of crazy that you can get all that grid out of one line, because that's actually super useful if you're, let's say, trying to sculpt some complex shape and you want to be able to visualize your 3D position. This is basically just painting based on 3D position. So that's super useful. And then you get into the two coloring modes based on normals and based on this basic lighting mode. So this bottom one and this top one, that are based on the quote unquote normal. And so if you're not familiar with normal, this is something that's like, the normal is basically the angle. If you put like picture something pointing directly out of the surface, directly perpendicular to it, that's the normal vector. How do we get the normal? Well, it's pretty clever. This function get norm, basically, once you've hit the object, then you just test, okay, well, what does the object look like a little bit set to the side in the x-axis, a little bit to the side in the y-axis, a little bit to the side in the z-axis. And that tells you what kind of curve that surface is making at that point. And so once you know what that curve looks like, you can draw the vector that is normal to the surface there, poking out from it. And that's basically what this says right here. So once you have the normal, you know what the curve looks like. Now we can do 3D lighting. And so this is just visualizing that normal vector. And you can use that to do simulated 3D lighting. And so this is a classic. So you've got like a lighting position right here. And so let's just put like, sine time and watch the light move back and forth. We'll do cosine time times 2. You can see it's the very beginnings of a convincing 3D light effect. And so if you look at Shader Toy and look at something like this one, you're going to see the same basic stuff. You're going to see some distance functions, spheres, ellipsoids, sticks. That's what he's using here. You're going to see a map function where he's doing all kinds of fancy work to use to turn these sticks and ellipsoids into ears, mouth, legs, because this guy's insane. And then you'll see this raycast function, and then we've got this render function. And so he's doing a lot more here to define different materials, different segments that are going to be colored differently. So if you hit the body, then color it yellow. If you hit the ground, color it green. If it's an apple, color it red. Or candy, he calls them. So, and then this is another really cool thing that you can do. Instead of using min to combine shapes, you can use smin, which is just smooth minimum. He's got the link to the article right here. So that's actually really cool and terrifying. But this is showing like the primitives that he used and how he shaped them before applying the smooth minimum function, which blends between shapes. And he's got a whole write-up on it. But the awesome thing about it is that, like, again, if you're doing typical 3D with like a normal 3D mesh, you can't just like blend between two meshes in this kind of super cheap, like this costs the GPU almost nothing to do. And it makes these awesome blob kind of effects. Like that's what this thing in the background is, this like crazy trippy tree growth. That's just using and kind of abusing the smooth min function, which is just awesome. So the last thing I want to show you is in here, let's say we wanted to paint a texture onto these. We can use the function text 3D. And so this is something Shane taught me. He's another shader artist. And it's a great technique for just applying a texture to something when you have a position and a normal. So down here, I'm going to take this 3D lighting, and we're going to say col plus equals text 3D. And it's going to ask us for a texture. I'm just going to leave that blank for a sec, comma, and we'll put in the position, and we'll put in the normal. And so for this texture, I could load in any image, but instead, let's use Syn Media. And okay, it's complaining, because N is not N, this should be norm. Norm. Awesome. And now let's put this back on basic lighting. And let's pick some media. That works. And if you want to offset it a little bit or change the way that, so like media is kind of tiling in a weird way right here, right? So like if I look at I don't know, you can just see the seam between the media where it repeats, right? So over here, come down here to media settings, wrap mode, click mirror. There we go. Now it's mirrored. And so boom, we applied media to the scene. If we wanted to kind of bump it up a little bit, maybe I'd put like a POW, feedback 3, 2.0, times 2, make it a little more intense. Yeah. And then if we wanted also this, like, you can look up, so this diff is like the diffuse lighting, amb is ambient lighting. You could add specular lighting. That's something that a lot of shaders on Shader Toy are going to use to like add kind of a shiny surface, right? Like see that shine? That's the specular lighting. So if you looked in here, you'd definitely see, yep, there it is, specular lighting, Fresnel lighting. They're all just kind of one-line things that you can add once you have the 3D shape and you have the normal to the surface. That's the critical piece. Okay, I'm going to show you one more fun thing before we get off Raymarching. And this is just total just like a totally messed up glitch. But it looks pretty cool. So just take rd.xy equals rotate rd.xy, and we're going to rotate it by, let's say, rd.z. Why not? Okay. So what exactly did we do? Not sure, but if you just introduce like a little rotate here and there into the Raymarcher, you can do all sorts of cool, totally screwed up, kind of glitchy things and actually get some really cool effects. So I would recommend that as well if you like playing with glitch art stuff. So yeah, have fun diving into Raymarching. Definitely use the smooth min function, use text 3D, and use these shapes and see what you can make. All right, wanted to run through some of these links one more time. Join us on the Discord. Always chatting about shaders. We can help you on synesthesia or honestly anything VJ related. Check out Creative Code Art. These guys are continually hosting workshops about creative coding beyond just shaders. If you're interested in other kinds of creative coding as well, I'm sure they have more workshops that would be up your alley. And then for GLSL, these resources are some of the top out there. Big shout out to Kishimizu once again for the shader tutorial. You should go back and watch the rest of that video because that's a great intro, and the shader you get to make by the end of that one is also awesome. Shout out to IQ or GLSL, the absolute god. He is the creator of Shader Toy and invented so many techniques, so many algorithms, and he makes also awesome YouTube videos describing how he sculpts some of those crazy Raymarch things. So check out his page for his articles, for his videos. They're great. If you are the kind of person that wants to sit down and read articles in order to learn shaders, you should check out the Book of Shaders because it is actually the best way to learn shaders. It's interactive along the way, so it's got like little interactive applets interspersed with awesome writing and explanations of basically all the things I had to gloss over in this actual session. Obviously, shadertoy.com, the #1 place to go look at shaders, play with them, find other cool artists, see what they're up to. Shadertoy is awesome. And I also want to shout out the interactive shader format. isf.video is the webpage. And interactive shader format is made by the same people who made VDMX, the Vidvox crew. And it's really the precursor to the synesthesia shader format. They really pioneered the idea of having just shader plus controls for VJing. And so this site is full of awesome work that is actually already set up, unlike ShaderToy, it's already set up with controls. So check out ISF as well. All right, y'all, we're done. Thank you for coming. If you learned something, drop a like, send it to a friend. That would be awesome. Thanks for sticking through to the end, and we'll see you at the next one. Cheers.